Okay, start again. Good afternoon, everyone, and welcome to the Transitional AI Research Seminar Series. Today, we have a presentation by the director of the group, Dr. Vikas Chandra, and one of his students, Junru Hua. They'll be talking about extreme value forecasting. I'll let Dr. Chandra take it over from here.
Thank you, Rathanil, for introducing us. So this research began about 2 years ago or so, and I thought about this idea a bit longer than this, probably 3 years ago. And this was Rahul Aluwalia. He's also a co-author of this paper, and we'll see this presentation later, I guess. So he began his honors thesis with me, and then he moved to the industry and got a job there, so there was no time to actually revise the paper. So then Junru joined the group with the master's thesis, and she took all the code and reran the experiments. And so it was in a way, it was a comprehensive work, because we have validated our results. Right, so this is our view. As usual, we'll give the background, methodology, results, conclusion, discussion. So a background, what is extreme value forecasting? It is about rare but critical events, right? So such as you have extremes in especially in environmental problems, weather conditions, for example, cyclones, floods, they are all considered extremes. Floods, so you do not have that much of rainfall, and over a short period of time, you have like a lot of rainfall, right? And so because in a large span of time, you record the data, but of the extreme values, you have very little data of that type. That becomes a problem in machine learning. So how can we, so if you make a distribution of the data, the extremes fall more on the tail of the distribution. And how do we ensure that machine learning models are not biased, and because machine learning models are generally biased to the data. The more data you give, the more it learns about that type of regions in the data, the type of training examples, and they will underrepresent the data that is not represented that well in the training process. And that's the problem with extreme values. So extreme value forecasting using deep learning models, it's a big challenging problem. And how do we do this? So in the past years, we've had as I was saying about the distribution, so you have exponential distribution, normal distribution, and extreme value distribution. You have we're looking at these tails of these data, right? So that's what extreme value distribution represents, the humble distribution. So there are different types of distributions for extreme values. So our goal is to build a relevance-based framework to forecast values in the time series. So generally, what the overview of this project was to use data augmentation methods such as the SMOTE, SMOTE-R, and GANs, generative adversarial networks, right, which are generally used to augment data for class imbalance problems. So the vision was more that use our knowledge from class imbalance problems and use that knowledge and apply it to time series forecasting, which is not very common. So we have a review paper published looking at the last 10 or 15 years of data augmentation and ensemble machine learning for class imbalance problems. The paper is getting very popular. Cited, we released code and data with that. And the idea was to bring some of those ideas and how can we solve or address the problem of extreme value forecasting to some level. So the deep learning models that we are considering, why convolutional LSTM and bidirectional LSTM, because in our group we have few papers where there's a paper about crypto price forecasting, and we have an evaluation paper about different deep learning models. 5 or 6 models were done in 2021, 2022. And there we found that these models are doing, in those papers, are quite good for multi-step ahead forecasting and generally time series forecasting. So what we want to, some of the research questions are, what methods are better in preserving the extremes across the different thresholds? How does model architecture interact with dataset characteristics? Can we reduce concept drift while improving the rare event accuracy? So these are some of our research questions, and we use a relevance function, PCHIP, that is used to define the extreme points, and we'll go into more detail later. So there's a traditional time series models such as ARIMA. They have limitations because they do well for linear and stationary data, but struggle with nonlinear and noisy time series. So here what we are having is nonlinear and noisy time series, which is data such as in floods and cyclones, right? Real world data. But on top of it, we have the issue of extreme values, right? And even within cyclones and floods, there are the normal floods, the usual floods, and there are extreme floods that you get. And in cyclones, for example, you're coming from Fiji, we've witnessed cyclones so much, so we need all this research to address some of the issues. And one of the major issues in cyclones, we have a paper under review, is called rapid intensification of cyclones, where within 24 hours of a cyclone, your cyclone becomes really strong. The wind intensity increases more than 30 knots. So that's an extreme event within a cyclone, which is by itself an extreme event. So these different architectures are there, which are the bidirectional LSTM is a version of the LSTM model, which is an extension of the recurrent neural network model, right? And LSTM essentially is a more comprehensive recurrent neural network with better memory cells that represent long-term dependencies well, which is a problem for time series data. And CNN and hybrid models. CNN, I mean, some of you would be more used to CNN's, of course, not the news network, but the CNN model for audio, not for audio, but visual recognition tasks, right? So you have a cat and a dog, you know, these type of data sets, and you have CNN models trying to distinguish between them. We have CNNs, different versions of CNNs have evolved, visual transformers and others. They are all, a number of them are being used for autonomous driving, for example, face recognition, different forms of image classification, video recognition, scene detection, and so on. So a lot of visual tasks, right? So how and why should you use it for time series prediction? Basically, CNNs, they have these convolutional layers, coding layers that have automated feature extraction, and they are usually very large networks with millions of parameters depending on the size of the data set, but the input data set, and implementing them for time series data, which is, we're looking at univariate and some multivariate data. These are very small data sets, but you could have, in principle, a CNN implemented for time series data. The advantage over conventional models is that it has its automated feature extraction and with the max pooling and convolutional layers, and that can be helpful. So the CNN and putting this convolutional part from the CNN layers into the LSTM, it basically has shown in our previous research and in the literature, it provides a robust multi-horizon prediction. So we are taking two of the best models for this problem. So the key concepts in data augmentation. What is data augmentation? Essentially, when you have a class imbalance problem where one class you have 90% and another class you have 10% of the data. That's an example of a simple class imbalance problem. You try to use data augmentation methods, and it could be simple methods such as SMOTE-based methods or others, which are some variants of SMOTE-based methods. You can use them to generate new data based on the minority class data, and they help in improving the training performance of deep learning models, because you are essentially increasing the size of the data. So that's generally for classification. So this is just an example, the overview of data augmentation. You have a sample of data, and then you have different versions of that data. And another version, another viewpoint is here. And all this increasing the size of the data, adding some noise to the data or some sort of interpolation to the data, looking at a small group or a larger group of the data, subgroups, and creating new data sets that help in the training curve. So that's the overview of data augmentation, and we have SMOTE-based augmentation. So SMOTE is a method for classification problem, and the SMOTE-R is a method for regression. So it's that's the R is for regression, and because regression essentially time series forecasting is a regression problem, so we use the SMOTE-R to augment the data. So now, just as in class imbalance problems, we have minority class and the majority class, and in extreme value, you could see those extremes as the minority class. So it was a very simple translation. It's not a big deal, right? So, but it's just a lot of work has not been done in this area. So we're like, okay, bring the deep learning, bring the extreme value theory, and put them all together. So that's SMOTE-R, and then we have SMOTE-R-bin, which addresses concept drift by partitioning the time series into bins of consecutive rare or common observations. Oversampling occurs only within the same temporal bin, ensuring interpolation with respect to local temporal dependencies and distribution shifts. So there are some more variations, some more improvements on the SMOTE-R. And temporal relevance by preserving short-term context during augmentation. SMOTE-R mitigates distortion of concept drift and improves the realism and consistency of synthetic samples for time-dependent forecasting tasks. So this is just an overview of classifying, bringing data augmentation based on SMOTE-based data augmentation. And so you have the majority sample is blue dots, and then you have the minority sample is stars, and you are looking at the minority samples here and trying to create synthetic samples which look the same as the minority samples. And then you mix them, and you have this, which is more of a balanced data set, where your previous minority samples are there, the synthetic minority samples are then part of this. So that's the SMOTE part is kind of seen. This is using KNN and using very basic machine learning models to create those samples. But then we have more deep learning models that are creating samples, synthetic data, and one such example is the generative adversarial network, and it introduces model-driven approach to data augmentation by learning the underlying data distribution through adversarial training between a generator and a discriminator. So you have the generator and the discriminator. This is just the overview. Generator is there, discriminator is there. You have these real images, and then you kind of perturb them with some operations that can be randomly done. And then you have your discriminator loss and the generator loss. And iteratively you train the model so that you can produce new data. So there are problems with GANs. I mean, the GAN approaches, they came into the field for generating visual data, image data. So in the 5 or 7 years ago, they became very popular, around 7, 8 years ago, for generating visual data. And it has kind of led to this whole, GANs have actually led the whole field or motivated the whole field of generative artificial intelligence. But now GANs are not used that much in generative artificial intelligence. We have visual transformers and other models are overtaking GANs. So you have Soros and all those other technologies, they are not using GANs anymore because GANs are quite difficult to train as well, right? So, but it has motivated the generative artificial intelligence. So it can be adapted to time series and model nonlinear temporal patterns and enrich array events, right? So similar to SMOTE, which was used for classification, but it has been adapted for regression problems. Similarly, GAN can be adapted. And there's a lot of flexibility, and when you have a lot of flexibility, then you have further challenges. And GAN-based augmentation often faces training instability and mode collapse. Stability and reproducibility remain open challenges, meaning yes, less interpolation-based approaches such as SMOTE are in extreme forecast. Right. So every time you run an experiment or a training session with GAN, the data generated will be different from a second run. And if you use the data generated, you need to really, if you are creating a reproducible research, right, you need to store that data and in order to have the same results. So that's all there for the background. Now we're going to the methodology. And the methodology, the first thing is data embedding. Embedding is essentially in the case of using time series data for using deep learning models, right? We need to break the data into small windows, small overlapping windows, the time series, and those small overlapping windows, they are the size of the window is given by D and the overlap is given by T. And those small for the n sequence length of the time series. And Bacon's embedding theorem basically says a D of 3 and a T of 2 is good enough to represent the original characteristics of the time series. That's what Bacon has proven. But we can always experiment with more the size of D. So in our group, we have been using 4 and 5 as well. And actually, that is more for one step ahead prediction, but for multiple step ahead prediction, you need to consider probably longer size of D. So the relevance function PCHIP is used to quantify extremeness. We define a relevance function that assigns each sample a score. Higher values denote more extreme behavior, right? So we have a function where the higher values denote more extreme behavior, and samples exceeding a relevance threshold are treated as extremes. So intuitively, it's you have this time series and you will have extreme values in a time series, and based on the relevance function basically says that those extreme values, we need to pay more attention to those extreme values. And those extreme values we can use to generate data. So Ribeiro, actually, he is behind, he's one of the key researchers, Ribeiro. We have cited his works in this paper for PCHIP, and he has proposed a number of methodologies for extreme value forecasting. So in order to do that, you select percentile ranks from a scale time series or compute corresponding percentiles and assign the relevance score. and fit a piecewise cubic Hammite interpolating polynomial. That's what PCHIP on that to ensure a smooth monotonic relevance curve between 0 and 1. So this may or may not make all sense, but I've told you the intuition. And now when we see this here, this part, then you can see this is your scale time series, and then you have you've seen the definition, and this is your rank, the percentile ranks, the percentile, and the relevance, right? And this is the Hammite function that they were talking about, and you have your relevance threshold, for example, given here, right? We are going to go more into the framework, and then we are going to, Junro is going to show the code that actually implements this part in the framework, then it will give you more information. It makes more sense. So the overview of the method, the relevance-based resampling workflow, define the relevance function, compute the relevance for extremes and common segments, and do the resampling. So Junro, I invite you to go over this and explain with the code. Thank you, Junro.
Okay. I need to. Can I share my screen?
Yes, please. Okay, we have to figure this out now. Okay, I have done a pause on the recording. So yeah, you can share the screen.
You have to stop sharing you.
I have to stop sharing mine.
Just click stop sharing up there. Yep.
Stop share. Right.
Okay, we can have
Just,
example. Can you see this?
The slide, you go back to the slide, just open the slide, and then you can come back. So you should have that slide as a tab. If you could have that slide as a tab. So you can show the slide and then go back to this. Can you open it as well?
Can you see this? I have opened the GitHub.
Okay, right, fine. I'll just turn on, continue with the recording. Yeah.
Okay. Okay. I have opened the code. Can you see my screen? This is the example of the back data set within the threshold of 0.7. And here we importing the data. We use is the back data set, which is a London merge point CSV. And here we set the forecast in the Conv-LSTM and BD-LSTM as an example. And here we import the prepare for the data, and here is the window embedding. We set the step is 5, and we set the split ratio is 0.07, and here we set the window embedding, and then here is our relevance function. The whole relevance function is be set in the relevance.py document, and here we run the function of that, and we the PCHIP percentiles is we cite the 25%, 95%, and 99%, and the PCHIP relevance is the 0, 0, 0, 0.75, and 1. And here we use the combine step as the first step, and then we got the KY as the variance like if it's the extreme value or it is a common value. And then this is the target. This is the plot of the target value, which is a distribution of the back data set. And then this is our resampling method. We can set at the SMOTE regular, SMOTE bin, or the more we can also use the GAN of the CNN and FNN. And here we use here we just run the SMOTE regular and SMOTE bin. And here is our GAN our code of the GAN method. And here is the code of the SMOTE method. We use the k-SMOTE neighbors as 3, and we run the resampling result. This is what our resampling code, which is in the resampling.py document. And what we import is this variance, and what we got is here. Here is this 3 resampling method, and what we got is the number of relevance, number of common, and the total. Here we got what we want to extreme values, and here is the plot resampling result. Here is what we use in different ways, like the blue one is SMOTE bin, the purple one is SMOTE bin T, and for the green one is SMOTE, it's the GAN method. This is a different distribution of the target value after resampling. And here is what we try. We try a lot of GAN method to get the perfect parameters. So here, after we got the resampling, we just run the forecasting models. And here is what our evaluators parameters, and this is what we try. And here is we use the 10 experiments, and this is our model to run the Conv model, the Conv-LSTM model, and the BD-LSTM model. And here is what the parameters. We use the epochs as 30s, and here is what we got after 10 runnings.
General, could you please go into the relevance.py and just give an overview?
Okay.
Yes.
Here is the relevance py.
Yes.
Oh, sorry. Oh, here. Here is our PSH IP relevance functions here. Yes. And
okay, that's fine. So we can go back to the slide. Is there anything you want to say, or should we go back to the slides?
No, that's all. Thank you.
Great.
Did I need to quit?
No, fine. I'll share it now.
Okay. So
yeah.
Yes. Yes, so we in that code we just use a 4 step. The first we use the chip to assign each data point a relevance score between 0 and 1, and then we apply a Hermit-based function to each sliding window to get the to get the maximum relevance and tell us how extreme value segment is. And third, we split the data into common and extreme part using the threshold like 0.07, 0.08, and 0.09. And we just show a 0.07 in the back data set. And finally, we use the resampling like the SMOTE and the GAN method to generate the synthetic stream samples while preserving the time structures. And then together this step, we get the core of our relevance-based resampling framework. Yes. So you can take this of the deep learning. We use the two of the deep learning, which is the convolutional LSTM and the BD-LSTM, which this two picture is our structure of the LSTM, which is like we use the, yes. And our evaluation is used as SER because the traditional regression metrics such as RMSE is just to observe all the data, but what we want is just extreme value. So our priority is to evaluate how accurately the model predict real and the high relevance exam samples. And SER is a metric that it's like deliberate the whole matter into the different parts. So we just choose like the 1% and 5%, 10%. This is all we try. So we can see the results after the in the result of this. Yes. And you can take over this of the framework, I think.
All right. Thanks, Junru. So just take over here. Right. So what do we see? So this is the entire framework, putting everything together. So the first step is that we have processing of the univariate time series datasets. We're just considering univariate, mostly univariate problems in this paper. So in step 2, we have already discussed the embedding part. And step 3 is the relevance function. You need to compute the scores and extract segments of the time series based on those thresholds. So this is what you see here. You see a time series data set here, and then you have the extremes marked in red, right? And that's the Q25, quantile 25, quantile 95, and quantile 99. And those are things that define the relevance, help define the relevance function and the associated thresholds. So the intuition is essentially to take these areas of the data, right? These areas, and use them to generate synthetic data. So you have more of these. This is the thing is, for those deep learning models and general machine learning, these are, when you will see some of the results, when we plot some of the results, we found in the literature and in all our past work, that these are the regions where the deep learning models don't do well. They are usually okay in these regions. But in the outer, they are the tails of the distribution. So the relevance function helps us to consider that. So we have the different deep learning models, which we have convolutional LSTM 2D, bidirectional LSTM, and we compare SMOTE-R, SMOTE-R-Bin, GAN, and convolutional GAN. So these are all these data augmentation models, and we want to see which are the best data augmentation models. And we train just 2 deep learning models to see which one of them are better. So as it is, this is actually a very simplified framework diagram of what Rahul had in his thesis, right? He had so many more models here and some other stuff here, and then it became too difficult for us to put everything together in one paper, and then we had to redo the whole thing. I mean, Rahul was very ambitious. He did a great work in his thesis on his thesis, but it was too difficult to break it down into a paper. So as you can see here, that we have, and because this problem is common in our group, where we have students, we give a project and there's just so many deep learning models, so many data augmentation models, and they're like, what do we do? And then students start doing everything, right? And then you have to cut it down, and then you're like, oh, the paper is becoming too long and experiments never end. And because of these things, we have these things here, these so many models, and then we have so many hyperparameters. Then you're like, okay, we need to now take a significant portion of our time to address what are these values that we should use here. So our strategy is just use whatever is in the libraries, right? Look at the literature, see what worked in the past for similar models. You don't have to spend too much of time improving these, because they may or may not give too much. And you should define your research to focus to some set of research questions and say, okay, this is not really the scope of my work. And usually in the review process, we get reviewers asking us, hey, how did you solve this problem? You need to have your justification. And this is what our justification is, that we use existing hyperparameters from related work. Otherwise, you'll spend one trimester or half a year just for the hyperparameters. So we go into the results now. This is the example of cyclone time series with beans corresponding to 0.7 relevance threshold. So that's the beans that we have that defines this. And this is actually the cyclone wind intensity in knots, right? Also known as the speed. But I know that you are saying that what type of cyclone is this? But this is because we have combined cyclones of 10 or 20 years together and just stagnated it next to each other. So concatenated that. And it doesn't matter what is the cyclone. The goal is that whenever the cyclone comes, the deep learning model should be able to predict the wind intensity. So we have these box plots, and you have these extreme thresholds visualized there. And then again, extreme thresholds, and then we have the relevance threshold visualized there. So this is the data visualization showing the TCHIP and the conversion between relevance threshold and extreme threshold, right? So now that we have all this, the setup is done, then we did experiments. Actually, Juru did all these experiments where we have the SER 5%. So SER 5% basically refers to, we just consider the RMSE of, these extreme values. Right? The RMSE of those extremes. We do not care about the rest of the 95% of the RMSE. That's what the SER is. And that's the general RMSE, and RMSER is there. Junro, what is RMSER in this case? The relevance. Junro?
There also the relevance.
So it's taking for the entire set of RMSEs?
Yes. The MSER real is the.
Or it's the REA. So
yes.
What is the REA? How is the REA defined? What I'm trying to ask is, what is the difference between RMSER and SER 5%?
It's the 5% is the 5% of the whole data, and the MSER real is what we defined as the extreme value, and MSER real is the whole extreme values MSE.
All right. So we comparing it with no resampling, where you you consider that there's no extremes, and the standard approach where you just throw in the deep learning model. So this is the RMSE, means that we want lower values are the better values. So you see that this is the worst. And at times when you're using data augmentation models and they are not really calibrated well in terms of the hyperparameter as well, you may at times generate data that is not good enough for your problem, and you throw in a lot of data that does not look good, and you use it to train, and actually it deteriorates your performance further. So if you can see in the SCR 5%, your general, even without any data augmentation, you had the test of training test of 0.1, but whereas this deteriorated further and this became really bad, 0.18. So in here, what we see is the training performance improves quite a bit, quite significantly if we look at 1D convolutional GAN, which is 0.05. But it does not really improve the test performance on that much. So the training and the test bias sometimes is there. But in general, we see other things, other RMSE rare is also improved the training when you compare to that. And here we have the RMSE rare has improved. So we have the SMOTE-R regular. The SMOTE-R regular has done better than the SMOTE-R bin, right? And if you can see the SMOTE-R regular in the RMSE regular rare, it has really improved the training performance, and it has slightly improved the test performance. And in this case, for the Cyclone South Pacific Ocean, it has improved the training and the test performance. And for difference relevance threshold, it has improved compared to the no resampling. And here too, it has slightly improved here and compared to the no resampling here and also here. So, and if you look at the general thing, which is the RMSE trained and test, you have the test performance without no resampling is not really that clear, because you have the 1D convolutional GAN actually is deteriorating the performance in this case, in this case, this case, in most of them for the RMSE, because the RMSE is considering the entire data set, whereas the RMSE rare and the SER, they are looking at more of the extreme values. So this model approach improves more of the extreme value, but not the entire data set. So we have the problem then applied to prediction horizon, 5 prediction horizons. That means 5 steps ahead. And in the Cyclone case, each point of the data set is recorded every 6 hours, 6 5 30 hours. So that's there. And what we see here is that the lower the values, that means it's better. And we see that the SMOTE-R regular is giving one of the best performance, and in the earlier time series steps. And then in this case, that's for the byte data set. And then later it deteriorates performance. But for the Cyclone data set, it is better than the rest. There's no sampling, no resampling. So in all of the cases in the Cyclone data set, this method works better. The SMOTE-R. So the overall trends that we see is it's also data-based trends, different data sets, problems of different characteristics. Since this method has worked better in the Cyclone data set, not done that great there. So SMOTE-R methods outperform GAN-based approaches. That's a major conclusion. Trend best performance observed at threshold 0.7. Accuracy towards test horizon increases. SMOTE or regular shows slowest degradation in store sports dataset stability. Method-wise, SMOTE are regular uniform interpretation of lowest RMSER, and it's stable across all the data set, being dense near threshold, strong at SAR, but SAR dependent. And again in CNN, FNN, oversamples fire right extremes, distorts global shape, weakens the long-term stability. So GAN, which is a deep learning method, huge, and it takes a long time to set up, a lot of effort. It's not really doing that great for extreme value forecasting. That's the take-home message from this investigation. And we look at some other data sets like Lawrence and Sunspot and Bike. We have seen some of the results already. And those similar trends are there when you see this. We're running out of time. And the South Pacific Ocean and South Indian Ocean. And these are some plots, further plots to visualize the pattern based on the different methods and the SER thresholds and the general RMSE trends. So looking at convolutional LSTM and bidirectional LSTM in the cyclone and bike data sets. So overall best worst model strategy combinations. So the best model, if you look at the Lawrence, the best models for most of them, for Lawrence and bike were BD-LSTM, Sunspot, Cyclone, SPO, NSO, convolutional LSTMs. And the best strategy was SMOTE regular, SMOTE bins are there, and at times there's no even, for some problems you shouldn't do anything, and that's what we are finding. And the worst is BD-LSTM in most of them. So convolutional LSTM is done great. And the worst performance is here. I think, Jundro, we have a small error in this table because we cannot have having the best and the worst. So you need to check and we need to revise the archive of this paper and improve this part. So we'll do a revision. So these are the key observations that we've already discussed. And the conclusion is extreme value forecasting is hard because it's tough. Deep learning models need data, but extremes are rare. And more recently, as I've been investing in crypto and other financial stocks, just trying to check how it works. And just recently, the oil price kind of fell down.
Yes.
And that's like an extreme event. And a lot of people invested in that. So, but it's coming up, and because that's it's not a univariate time series. You see that the oil price falling down is based on the Hamas and Israel-Hamas war, and basically they're coming to a peace plan. So the demand for oil will lower. People are more relaxed that there will be an oil supply more easily coming out from that region. So those are the other things that kind of affect the price. So in terms of weather patterns, cyclones, floods, there are a lot of other variables, and it's tough to actually know what they actually, those variables really make, if they make a significant difference or not, because we have another paper which is under review and also on online, which looks at the sea surface temperature of cyclones for the last 30 or 40 years. And then it tries to find if the sea surface temperature, the rise, because the last 30 years we have the rise of sea surface temperature and how it affects high category cyclone formations. And based on that, it was difficult for us to really come to strong conclusions about the sea surface temperature. So the thing is, because climate change problems, you need data for a longer span of time, and the data, how accurate is the data, and so on. So it's all about the accuracy of the data, not just the accuracy of the model. That's another issue. So resampling helps, SMOTE-R regular is more stable, while SMOTE-R enriches the threshold region without breaking the structure. The best strategy shifts with forecast horizon. Model beta strategy alignment matters more than model size. So BD-LSTM fits periodic stable series. Convolutional LSTM fits suits a regular, not stationary data. And the key limitations are the definition of extremes. We rely on PEC HIP-based relevance function with discrete thresholds. While consistent across expense, threshold sensitivity differs by the data set. And we actually saw that in our experimental results, where some models had better results for 0.7 and some had better for 0.8. So it's good to look at different extreme thresholds, right? So, and I think our experiment setup, Junru has done a great work by considering a smaller set, because we have thresholds, then we have the models, then we have the data augmentation strategy, and then there's just too many combinations of things, and how do we come into general conclusions? And I think this paper is quite a good paper in the experiment setup that shows, gives a pathway for when there are too many things, too many models to test. So generative augmentation scope, only 1D GAN and 1D convolutional GANs were examined. Observed instability likely reflects architectural and optimization constraints. The broader capability of diffusion and transformer-based models for AI events synthesis remains unexplored, which can be direction for future work. And I've already said some things about the data set. Its dependence is there. And the other thing is the noisy time series and the sparse byte leading to unstable behavior and limited generalization. So the future directions are ensemble-based forecasting. So one thing is to how do we integrate these architectures such as convolutional and bidirectional LSTM, because you see there's some problem, one was better than the other was better, and also the same with the data augmentation methods. So we need to really brainstorm how to combine all of these so we have a stronger model, which is an ensemble that can apply to a wide type of problems rather than one or two problems, and we have to calibrate for those problems. That's a tough thing in machine learning, but something that we need to think about. Maybe we need a meta machine learning algorithm that works with the ensemble learning to do that. To actually a meta machine learning model, which I mean with ensemble learning, something that looks at the data and decides which ensembles to give more weights to, which ensemble models to give more weights to, right? Either the BD-LSTM or convolutional LSTM, because based on past experience of those data types. So there is some, because in ensemble modeling, you have ensemble models, for example, begging or begging, you have a group of ensembles and all of them, make a prediction, and then all you do is summing up the predictions and giving some weight, which is equal weightage the predictions. But here, if we want to really develop a strong ensemble type forecasting model, we need to really think about what weightage to give to each type of model in the ensemble. Domain-aware learning, embedding physical or regulatory constraints into deep models can enhance stability, interpretability, and stability. Physical consistency in environmental prediction of financial risk principles can guide learning with realistic boundaries. So we have this physics-aware deep learning as well. And we are doing some of that. Arpit Kapoor is exploring more of that in our group with hydrology and hydrology-based models. Uncertainty quantification, critical Bayesian and bidirectional approaches, and integrating these with relevance-based models to improve reliability. So I think all these three can be each by one paper each for the honors and master's students if you want to explore these other topics. So thank you, and special thanks to Rahul Alvadia, who has contributed to the earlier version of the paper. And our code is in GitHub repo, but we are going to update it and have another repo, and that will be linked to our archive and the list of the seminar series there. and references. Thank you. All right, sorry, we're running out of time, so we'll take two quick questions.
I have a question.
Yeah.
Yeah, am I fine to ask?
Yes, yes, please.
Yes, okay. So I've actually got two questions, but I'll start with the last one, which was when you're suggesting using ensemble methods. Depending on how you implement the ensemble approach, you're likely to, a lot of ensemble methods are based on averaging, so you're likely to eliminate the extremes, right? So how do you reconcile that type of ensemble modeling approach with trying to predict extremes?
So you are saying there are different types of ensemble learning and sorry?
Yeah, because some use voting, right?
Yes, yes.
And some use averaging. So if you're using averaging, that's going to push things towards the common values, and you're going to eliminate the extremes. So the extreme values. So if you're trying to predict extreme values, ensemble learning, if you're using averaging, seems to work against that.
I think that's a very good question or comment to really explore that part where if we're developing some sort of ensemble, that's something we need to really explore.
Yeah.
Voting and averaging in the times of extreme value forecasting.
Yeah.
I think that's a more simpler thing to really explore when for honest thesis level work.
Mm-hmm. I have a second question, which was about the implementation of the relevance function.
Yeah.
If I understood that correctly, you've simply used a numerical representation of the relevance function, right? You've got these numerical values, and then you compare those numerical values to the threshold. Could you do that with a mathematical function? So an algebraic representation of the relevance function, and then simply sample from the function.
I mean, at the end of the day, you need real values, right? So it doesn't matter where the real values come from, right? So if your function,
so
this function, right?
Yeah, so you could, I don't know, because it's essentially a cumulative distribution function, the way you've got it, right? So if you specify some standard cumulative distribution functions instead of the numerical values, then sample from those functions to do the comparison. I'm wondering whether that would produce any insights.
Yeah, I mean, the function will have some effect on it, but it's like one of the things is like how logically consistent the definition of that function is given the actual time series problem, extreme problem you are looking at, right?
Well, if you use a Gumbel, like a cumulative Gumbel.
Yeah, perhaps, yeah. That can be explored as a direction of future work.
Yeah.
Looking at the relevance function.
Thank you. Yeah, good answers. Thank you.
Great, thanks. Any other question?
I think that last question from Renee is like really interesting.
Yeah.
You mentioned the mathematical cumulative aspect of that. It might be something to infer and see the inside. Instead of using number threshold, we have a cumulative threshold to actually look at.
Right. Something for you to.
Not me. I'm not in that area, please. I have a lot of things.
Yeah, I had a similar kind of thought to that, Rodney, because to some extent, when you're trying to predict extremes, it's almost like the phenomenon you're looking at actually consists of two distributions: the distribution of values under normal conditions and the distribution under extreme events. And so you don't necessarily want to predict points that are sort of at the extremes of their standard operating distribution. You want to predict the events when it's moved into a new distribution. So it's
well, that actually suggests another way to look at this, which would be to use mixture models, right? So
Yeah.
mixtures of distributions. So that would be another way from a statistical perspective to go with the type of extension I'm thinking about.
Yeah.
Yeah.
The problem is you've got to fit those mixtures of distributions to the whole data and then predict when you've moved between the distributions.
No. In this case, it's the relevance. It's the relevance function.
Oh, right. It becomes a mixture.
So
Yeah, okay.
you're imposing that on the model externally. You're not fitting it, as I understand it, right?
Yeah.
Yeah. So what you then want to know is, okay, well, if I use a Gumbel, and sample from the Gumbel, so use the Gumbel for the relevance function, sample from it, do the results change? And how do they change? If I use a mixture of distributions with a Gumbel and some like a normal combination, and then sample from that, then how do the results change and do they change, right? That's what I'm thinking.
Yeah.
Rodney, if he puts the normal distribution with Convo, what's the probability it's going to get the extreme values? Because I don't think normal distribution goes that deep with extreme or Convo. Yeah. I don't know the compatibility of the two of them.
So the normal has an infinite range, so it can, in principle, it can handle extreme values.
Okay.
But the tails of the normal aren't fat-tailed, whereas the Gumbel is going to, depending on the extreme, if it's an upper or lower extreme, depending on how you do it, is going to have be a fat-tailed distribution.
Oh,
right?
I think correct. Yeah.
Right.
Yeah.
But John's point, I think, is quite correct, right? In that the splitting method you use between common and extremes is if you in a sense you could reflect that in the way you define the relevance function by using a mixture distribution.
Yeah.
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 That's my thought. So the question is, is this I don't know if it's a good idea or a bad idea. You would have to try it and see what would happen, right? Yeah.
I had another kind of like question / suggestion related to that, which is that, the results, you've shown a lot of results for a lot of data sets with a lot of variations. And even though you're saying the SMOTE-R regular is the overall winner, there was still a fair bit of variation in there. I wonder how much of that variation is driven by the underlying distribution. So like a follow-on work would be, you have more data where you know more about the different distributions and you're saying, given these properties of a distribution, this is the right data augmentation approach to take. Does that make sense?
Yeah, it does. But I mean, the table at the end was interesting because this is a really good example of the no free lunch theorem, right?
Yeah.
Right. So in a sense, that's what you would expect to come out of the question you just asked, as well as this type of analysis, right? Some methods are going to work better for some data, and some are going to work not so well for that data.
Yeah.
Yeah.
If you
Oh,
look
sorry.
at the time series examples that we have, like the distribution or the extremeness of those time series problems are quite different. Right. So yes, the node free theorem comes into play, right?
Yeah.
For example, we have this is cyclone, and then the bike one looks quite different.
Yeah. Yeah.
It's not here, but it's in the paper here. So it's almost like comparing a wine classification dataset with iris classification dataset.
Yeah.
But
I guess the hope would be if you can characterize the distributions in some way that gives you a little bit more insight. You wouldn't get a free lunch, but you might get a free biscuit.
Maybe using program.
I think we are getting a free biscuit if you look at
I want coffee with that.
Right? There's a biscuit somewhere, but yes, no free lunch. Yeah, definitely.
Yeah, that table there is essentially showing the no free lunch result, right?
Yeah.
Yeah, which is I mean, I think this is really interesting and really good work. So yeah, congratulations.
Right. So many thanks to Junro and Rahul Aluwalia, and thank you everybody for attending. Thanks. Junro, is there anything you would like to say before we switch off?
Oh, no, thank you so much. I think you helped me so much. It's really patience about, I mean, you know, you're the expert of this area, and I learned a lot in this paper. Yes. So thank you so much.
Thank you, Junro. It's a pleasure working with you. Thank you. See you. Bye-bye, everyone.
Bye, everyone. Thank you.
Bye. Thank you. Really interesting.
Bye.
Bye.